and I'll confirm you. We can start.
Right. Hi. Good evening, everyone. I hope you're all having an inspiring and insightful week so far and a great day. My name is Gajendra, and I'm thrilled to be your host for day 4 of Tech Week 2024. This week has been a remarkable journey filled with cutting edge discussions, innovative ideas, and invaluable networking opportunities. And today promises to continue that momentum. For those of you joining us for the first time, welcome to Tech Week, a gathering of brilliant minds from across the tech industry, where we deep dive into the trends, challenges, and future of technology. Whether you're a seasoned professional, an inspiring entrepreneur, or simply passionate about tech, there's something here for everyone. Let's quickly recap what we have covered so far. Over the last 3 days, we have had the privilege of hearing from industry leaders on topics ranging from generative AI, blockchain to AI security and governance. The insights shared have not only shed light on the current state of technology, but also provided a roadmap for where we are headed. Today, we are going to shift gears and focus on some of the most exciting developments in AI and machine learning. Our speakers will explore how these technologies are revolutionizing industries with a particular emphasis on marketing, analytics, AI architectures, and the future of AI-powered systems. Without just a little bit introduction before our first speaker starts their session, right? Our first session for today is Arva Kumar, right? He's a machine learning manager at Adobe, where he oversees the development and deployment of machine learning services across various Adobe products. Sai has built machine learning solutions that leverage generative AI to address challenges in domain-specific question answering, SQL generation for data retrieval, and tabular analysis. Active in the machine learning community, he holds several patents and has published in top machine learning conferences, including KDD. Please join me in welcoming our esteemed speaker, Sai Kumar Arva. Over to you, Sai.
Hey, thanks, Gajendra, for the introduction. Thanks for the CloudxLab for this opportunity to present. I'm super excited to talk about my team's work and what we are doing in the field of generative AI and marketing applications at my work. Let me share my screen. Can you see my screen?
Yes.
Okay, great. So today's topic is about improving the capabilities of large language model-based marketing analytics copilots with semantic search and fine-tuning. As we see with the introduction of ChatGPT around 1.5 year or November 2023, we have seen a huge influx of usage of large language models, both in consumer applications as well as enterprise applications. And we have also seen tremendous value unlocked, mostly because there are a lot more use cases that could be done in a much more faster way with the use of these new tools. In this, with this perspective, I'm going to talk about how we can leverage these large language models in the domain of marketing analytics. And we will further deep down into how fine-tuning and semantic search improves that even better. Let me introduce my team. So Yilin, Yanchen, and Jim are part of my team and have done some excellent work on this topic. So before I go ahead, just if a fresher on the LLMs. So it all started with one of the papers, Attention is All You Need, around 2017, where the transformer architecture was introduced with a significant performance increase uh, in next word prediction. So here, as you see, LLMs have these concepts of embeddings where we index categorical variables into a numerical representation, which was pretty famous even in Word2Vec. But now it was used along with some other concepts such as masked multi-headed self-attention. The self-attention is a function of query key value. Query key value are the concepts taken from information retrieval field, and they have always been there. However, as you see here, the query and key are multiplied, and a softmax was taken on that to get us the self-attention. Similarly, the multi-headed attention would multiply with both query key vector with each word. Uh, Once we have these vectors around both uh, the attention, self-attention and multi-headed attention, it helps us get a uh, virtual idea of how important each word is towards the prediction. And masking is what it means. It means is literally zeroing the contributions from words that occur after the current word. So these are the concepts that are introduced again in this paper, but have influenced how it performs in terms of text generation. So now that we just went through what the transformer is, now we will talk about why large language models could be useful for marketing analytics. In the field of marketing analytics, the persona who usually interacts with these analytics tools are mostly the marketers who do not have access to a lot of tech stack and would rather be comfortable interacting with a much more simpler user interface rather than writing a lot of uh, SQLs or even some Python versions of code. And even there, nobody wants to do a lot of data crunching. And in an ideal world, they would just want to ask a question and get an answer. So the way LLMs are useful is it reduces the amount of effort required to answer human questions. We will talk about a bit shortly. And it also provides more flexibility in insights beyond static dashboards. And it can make information lookup for efficient for customers and can help resolve challenges more quickly. So the way LLMs are doing this is either it could provide a natural language to SQL kind of transformations by helping the take a question as a text and then converting into a SQL and running it in the background and then providing an easily consumable output for the user rather than a group of 10 links that the user has to go through and then understand or decipher. Instead, sometimes even the analysis part it can be done by the LLM, or sometimes it could just be the information retrieval, or sometimes it could be the both. Now, before we go into some problems with LLMs and how the industry is tackling them, this is a picture generated through Adobe Firefly of with the prompt, a robot writing on a chalkboard with the equation 2 plus 2 equal to fish. So this shows that the world of image generation has evolved significantly, and it's a lot more easier for creative professionals to generate images by just providing a prompt in the early days, it would have been near impossible to generate this image with such perfection, but now it could be generated at just one single prompt. Similar improvements have been used in different domains to extract insights from huge databases that are hidden from marketing persona. So the problems with LLMs are not in particular to marketing domain. For example, the context length limitations. For some of the OpenAI models, we still have a context length or the limit of 32,000. And for the latest Gemini models, we do observe something around 1.5 million tokens. However, if I have an extremely large repository of knowledge, which has millions or even billions of tokens, in that particular case, it's not feasible to expect any large language model to do a good job at answering my question. So that's the limitation that we still have even today. But there are some workarounds on how to still get an answer. The second one is hallucination. Hallucination is one of the most challenging problem because of which most applications, especially the enterprise applications that need 100% fact-based accuracy, are difficult to get. Hallucination is defined as a problem where it confidently returns inaccurate information. This is especially true, more likely to do so with more complex tasks. The way LLMs are trained is always based on historical data, and the large language models learn how often the words come together, and so that they could predict the next best word. In cases where they haven't seen any question that is being asked, it has to come up with the best answer, and hence it tries to recollect from its memory and gives a most plausible answer. However, that's not always the correct answer, and hence we see large language models ending up returning inaccurate information. This is dangerous because in enterprises, business decisions are made based on what's the information, such as either revenue or ROI or cost or similar metrics. And any incorrect information can lead to very bad consequences. Hence, it's super important to tackle hallucinations in enterprise use cases. Mathematical illiteracy is a third challenge. And large language models are primarily trained on text, a bunch of keywords, so that they could predict the next word better in a large corpus of text. However, no training was done on numbers or any math formulas or etc., because of which they could not understand the numbers so easily. And this problem even goes deeper for floats precision. So we have often seen a lot of examples on the internet where folks would ask simple questions or simple mathematical calculations that a elementary kid could do, but GPT fails at it. This is the reason because large language models are not trained to handle the mathematical calculations like a calculator does. So, however, in enterprise situations where you have to do an analysis with a bunch of numbers, the large language models fail at this. Finally, the interpretation difficulty. So once I have a bunch of output from these large language models, it's very difficult to understand the output produced for the LLMs because either it doesn't understand the context or sometimes it doesn't understand what we are looking for. And it's also difficult to tune without creating new problems. Maybe we will talk about fine tuning later, but basically, fine-tuning is where we are trying to improve the current version of the large language model so that it handles the data that we have better. So it is a domain adapted large language model where we are changing the model parameters for the last few layers of the neural network so that we would be able to better or predict with increased accuracy for newer domain. And there is the problem of bias, which might not be affecting the enterprise domains, at least in the field of marketing analytics. So, however, bias is still an important topic because where we produce pictures, we do not want images to be reflected of certain demography or certain gender or race, because of which we have to be extremely conscious of what uh, training data goes through to these LLMs and whether it reflects the current world biases. In the past, we have seen that some fine-tuned LLMs have reflect corporate biases, where some models have over-indexed on uh, removing the bias to the point of uh, removing the complete factuality. So, while bias plays a super important role, especially in B2C applications as well as in the world of generating images or text for marketing applications, where the primary use case is around natural language to SQL or the analysis of the data, we might not have this particular issue. So let's talk about prompt engineering, which is one of the most easiest ways of invoking these large language models. Earlier, large language models could only be used by programmers who have the skill set to either import the library and then add a bunch of context around it, and then train the model a bit by giving some examples, and then uh, give it uh, give it for some use case discovery. However, the zero shot and one shot use case, the research has significantly progressed, and then came the ChatGPT, where amazing amount of information could be retrieved and analysis could be done just by prompt engineering. In this slide, we show how a typical prompt engineering workflow works. As you see, a user could ask a question to, let's say, some ChatGPT or GPT-4, which is the pre-trained LLM. In this case, what it does is usually it does the routing first. And the routing is where it decides whether this question is a question answering question or an SQL query generation or a tabular analysis or something else. So these are the tasks that help the router to assign which kind of question this should be assigned to. Now, once the tasks are defined, then it goes to the list of tasks and see if it could be one or more. For example, for some complex questions, probably we want to get through all the question answering, SQL generation, and tabular analysis, and even visualization. So it has to combine all of these tasks and look at the prompt end to end. So the prompt design is a critical step in it. While it's been 1.5 years when ChatGPT has been introduced, a lot of research and articles have been written about how to design the best prompt. Some of the best practices is to provide plenty of appropriate context and to consider the edge cases to get the best possible performance, and to even specify some examples and output and be clear and specific and avoiding bias, and use complete sentences and giving proper instructions and including at least few examples for the model to understand what we are looking for. And once we have designed a prompt with all these aspects in it and provide it as input to the pre-trained LLM, then we would get an answer that could be used for the business. So this has made it, the prompt engineering has made the large language models extremely useful even for a non-programmer, which helps uh, move the field really fast. Now let's talk about the semantic search. This has been, this is the next level of tooling or the techniques that could be used in conjunction with large language models. So in semantic search, because of the limitations such as the context length limited to either 32,000 tokens or even sometimes a million tokens, we would want to store all our documents in a database. For example, if I have a million documents, and if I want to query over any of these documents anytime, the fast way is to use some kind of information retrieval through Elasticsearch, and especially do some kind of keyword search, and in some very sophisticated scenarios, usually do a semantic search. However, with uh, the concepts like retrieval augmented generation, uh, where we leverage the semantic meaning of the question we are asking with some chunks in each of these documents, we do see improved performance over very large corpus of data. In this case, the way it's done is just chunking each of these PDFs. Probably each chunk could be a size of 2000 words. And for each chunk is stored in a database. And whenever a user asks a relevant question, then 10 or more chunks relevant to that question, which have near semantic meaning, would be extracted and then provided as context to large language model, which will then synthesize these information and provide an output. So basically, all the semantic search and the RAG approaches are doing is they take a question and then pick the appropriate chunks in your entire database, and then using the large language model as some yeah, to get the output. And this is the most popular approach for knowledge discovery or for question answer in the current day, because it's also one of the cost-effective methods, because here we are using only some kind of vector databases to ingest or store the information and do a quick semantic search. Semantic search is different from keyword search, where we instead of doing the exact keyword mapping, we use some kind of embedding difference. The one of the most popular algorithms is invented by Facebook, which is FICE, which does a very quick semantic search. And then fine-tuning is one of the last approaches where we see that, hey, no matter what we do, even retrieval augmentation could not help us, because there's a lot of domain-oriented text, which is extremely specific to us, and we also do not want any hallucinations. Then fine-tuning is one of the approaches where you have a small labeled corpus, which is my domain data, upon which we are fine-tuning. In this slide, you see that there's a large unlabeled corpus which helped in training the pre-trained LLM. And now we want to update it with our small labeled corpus. And the way we do it is using some new techniques like LoRa, where we have the pre-trained weights, and we update these pre-trained weights by taking a projection of these weights into a smaller dimension space and only updating those weights until we are confident that it could handle questions on the smaller corpus. And now, once we ask a simple question on similar tasks pertaining to my domain, the fine-tuned LLM is supposed to give a better answer compared to pre-trained LLM because it has seen the new data and hence could understand the nuances in this data better. So some other details in the fine tuning is instead of changing all the weights, we freeze some of the weights in the few layers and then update only the weights in the last few layers. So that's for the literature, what's existing in the industry and how it could be leveraged for not just marketing application, but for any applications. So this is now what we have for domain-specific question answering. When we did these experiments, we had llamas and falcons and the GPT-4 at the top of the performance. And when we compare across different dimensions, such as the accuracy, relevance, thoroughness, clarity, and conciseness. And as we see here, GPT-4 does a pretty good job in most of the aspects. And especially the GPT-4 semantic search also does even better than the GPT-4. The open source model Falcon and Llama do a decent job in comparison with the GPT-4 semantic search. So the evaluation score is very important for any task, especially some question answering tasks, because it helps it helps to determine which model should be leveraged in the production use cases so that we could get a better performance and user experience to the end users. We have also compared the embedding models, such as the text embedding one and the instructor large and the instructor Excel versions. In this case, we also observed that for accuracy and relevance, the text embedding and the instructor large were almost comparable, but the instructor extra large was mostly not so great, but the first two were of similar performance in all the dimensions, such as the accuracy, relevance, or thoroughness. Next, we go on to the SQL query generation. The SQL query generation is the most important for any kind of analysis tools or the analytics tools. While most business or marketing folks might be comfortable with SQL, however, complex SQLs still need an understanding of how it works and how the efficient joins should be and how the schema of the underlying data is. All that information still needs a skilled persona to extract insights from, and hence SQL query generation is an important task that we can leverage large language models from. And the accuracy for SQL, again, as seen here, the fine-tuned Falcon has the highest accuracy, followed by the fine-tuned Llama. And then, interestingly, the few-shot learning GPT-4 did decently good because probably it was trained on some similar-looking data. And then the tabular analysis is where it's a very interesting use case because given a bunch of CSV or an Excel sheet with a bunch of values, we would want some of these large language models to provide us some accuracy in terms of the analysis. For example, let's say if we ask some question on, hey, give me the top two leaders in this sales analysis, or give me a summary of what's happening in this table. Those are the kind of analysis questions. And here, as we expected, because there's a bunch of problems like hallucination, GPT-4 in combination with LangChain Pandas does the best performance, followed by the fine-tuned Falcon. We have also resorted to quantization for the sake of optimizing our compute and the runtime. So even the quantization is model is still performing and giving a decent accuracy as we see here. However, pre-trained open source models don't do good at all, while the GPT-4 with some templates do again reasonably. The point here is to notice that in cases where we want 100% accuracy, it's good to combine a large language model with a deterministic function like LangChain or Pandas, or some kind of mathematical functions, so that we do not we use the right tool for the right analysis, where GPT-4 is only being introduced or being used for the transformation of the text to the Pandas input, and Pandas does the complex job of inferring or the analysis. So the closing thoughts, since we are close to the end of the talk. What we observed overall is large language models paired with semantic technology work well for domain-specific question answering. And this is being used by more and more big enterprises as well as startups everywhere. And results are not very sensitive to different embedding methods. So just verify for your application if the results are sensitive to the embedding methods. Otherwise, you could use any one of them. The debate between the prompt engineering, retrieval augmentation, and fine-tuning still continues, but there are very few use cases for fine-tuning, such as the fine-tuning improving SQL generation dramatically, especially if your domain is significantly different from what the large language model is trained on. And for the same reason, fine-tuning also improves the tabular analysis dramatically. And specialized agents like Pandas may still outperform fine-tuned LLMs because we haven't yet figured out the architectural changes that are required to make sure the large language models can have the logic built in to perform the math calculations yet. So until then, it's good to use special agents like Pandas. And finally, there's a huge discussion on the open source versus closed models. With the release of the latest Llama 3, I think a lot more could be done with the open source models instead of leveraging GPT-4, where we now have a flexibility and control, as well as the stability of output. Because if it is hosted on a third party where we do not have the control on the model, it's very difficult to have a say on the flexibility as well as the control, either on the usage or on the number of queries or the kind of output. And even the output could change whenever the model gets updated. So the stability of the output is better if it is controlled by yourself. And definitely the security and privacy. If you have the data, sensitive data that you do not want to send to third-party platforms whom you do not trust, then you could have security and privacy, but just hosting on your on-prem or in your VPC. And finally, the cost. In some cases, the closed source models are cheaper because they have the scale advantages, because of which they could offer at much cheaper price. However, in larger cases, in some cases where the company have a huge uh, uh, use cases, then they might explore hosting on their own and do some optimizations to reduce the cost. That's for the end of my presentation. Thanks for giving an opportunity. Any questions?
Yeah, yeah. Yeah, thank you so much, Arava. Like that was a really nice explanation. You started with explaining the importance, like you started with LLMs, like what exactly they are and the importance of it, and then like how it helps in making the decisions. But yes, there are few questions which we collected earlier and some in the chat, and like which basically we concluded few questions. So there will be few questions. If you permit, I'll proceed with that.
Sure.
Okay, okay, great. So the first question basically comes related to the marketing and analytics you talked about, right? So
Yeah.
I would like to understand like how LLM enhance those marketing analytics part. Like what specific advantages do they offer? Do they provide over the traditional marketing analytics?
Sure. Yeah. So, as we all know, the marketing analytics is a huge domain because every business needs marketing, and also analysis needed to make it more efficient for the business to run successfully. However, in the past, either the marketing analyst was done by two persona or two people, one with the marketing skills and one with the analytics skills, or someone, the marketing skills is someone who is good at understanding the business, and the analytics skills is someone who is good at maybe SQL or visualization dashboards like Tableau, Power BI, or even if was big data databases, then somebody familiar with Spark, SQL, or very fancy query languages. So this, because of the knowledge required, uh, there's a lot of cost associated with hiring these two different personas, or having a skilled persona with both this knowledge and expecting them to come up with an answer in a short amount of time. Uh, so large language models have uh, at least made it a lot simpler by uh, making the world of marketing data easily accessible to not just marketing persona, but to even the decision maker themselves. So now they don't have to rely uh, on the marketing personnel for every single question. Instead, they could directly approach these tools and ask a question in natural language like English, and we expect the tool to do the transformation behind the scenes into some SQL, uh, and then produce an output that is easily consumable again by the decision maker.
Wonderful explanation. I guess that is what LLMs are like providing. Like they are basically, because everything is in some or other language, which marketing personals or like other personals who are not equipped with the technical knowledge, right? And they find it very difficult to get the results in very quickly. I believe they have to reach out to somebody from the analytics team or from the tech team to get things done. Now they can utilize these tools because I think they are pretty much very close to English. Like very close to English is what like these are LLMs, right? So English only.
Yes.
Uh, like
Yes.
the human languages. Anyways, yeah. Thank you for
Yeah.
the explanation. One more question is like as you discussed about the SQL part here, right?
Yeah.
So what exactly um are the challenges for the SQL query? Like how do we take care of the accuracy. So how does this work with the SQL? Are we giving the schema to the LLM, or like how is it happening?
Yeah, that's a great question. So there are multiple ways to do it. So there's one way is we have seen in the industry, there's a lot of models which are trained only to get the best possible SQL. Uh, so the way they did it is they have trained it on a lot of queries and the schemas, so that the large language model is able to understand what's the appropriate SQL for a given query. That's a interesting and intuitive way of getting a utmost accurate SQL generation. However, if I have, let's say, more than uh, 20 or 50 tables in my data schema, and I still expect my large language model to perfectly frame an SQL, then it might not be straightforward unless you could put every single detail about the schema in your context length. For example, let's say you have a table schema, and each table, if it has, let's say, 20 to 30 columns, then you have to put these columns along with the descriptions in the schema, along with descriptions as the context for each of the table, and hope that the large language model could decipher what it is and could generate the SQL. This is where there could be potential problems, mostly because uh, a same column could be column name could be used in multiple tables, or a same uh, because the semantic search is not properly done, a column name that's not labeled properly is cannot be referenced. For example, something like pin code or zip code is labeled as a region code, and the large language model has to figure out if the zip code corresponds to region code, etc. So these kind of unknowns will make it difficult for just the prompt engineering to make it work. And this is where it's important to break down the text from the user into some kind of entities, and then make sure that we have a perfect mapping from the user's query into each of these entities, so that we get a near accurate SQL. And however, even before surfacing it to the end user, it might be more useful to run this query behind the scenes, and to see if it gets the relevant output. If not, make some changes or try out the next possible alternative until we get a reasonable user. At the end, however, since we cannot guarantee the 100% accuracy to this approach, it's good to surface the SQL or the query used, so that the end user could still take a judgment call whether the query reflects what they have on their mind.
Hmm. Correct, correct. In this explanation, like it was a really good explanation. You explained very thoroughly. But as you talked about the context limitation, right? So how exactly, like, see, I when I come across these kind of, like, I was trying my hands on the similar kind of problems. So the thing is that giving the schema in a prompt is pretty difficult, right? Like when it comes to the production level databases, the schemas are pretty big. The schemas are pretty big, and the another problem which arises is basically the table names. So table names are pretty uh, company specific, or let's say team specific, what they decided to keep it internally, because database was always internal, right? It was never designed in a way that it would be public. It is just designed in a way for the developer experiences, that okay, somebody else would be able to understand it, right? But LLMs, I believe, is that, like, if say I'm using a table name for something, and the generic English name is something else. So how do they ensure that Okay, so these are like completely two different questions. So how do the LLM handle that part? And the other thing is the context limitation. So how
Yep.
can we like fix that part also?
Sure. So for the context limitation, the yeah one that's why the bigger, larger language models like Gemini have been introduced, where you could uh, put much information, like even around more than 100 pages with 1 million tokens. So you could add a lot more context. But if it is something like GPT-4 where you still have a limited context, then one way is to break the problem into smaller pieces where you would have to identify uh, all the tables that are relevant. And for the question that you raised, where the table name doesn't help us with anything, then adding a description and some examples for the large language model to learn what this table means and uh, what what it does, and even possible some examples on how it could be used, will provide some information to the large language model that, okay, so and so table X means user table with the IDs and their activities, etc. So giving a lot of relevant information, some kind of description about the table and the columns and some few examples would help mitigate this issue where the table name is not appropriate. Same with the column names. You have to give some a description and some examples so that the large language model could get these correctly. But while we are doing this, it could be possible that we will run out of context length, in
Yeah.
which case we have to break the problem into multiple parts and get each table name correctly, and then figure out how to join these tables again through a different LLM API call.
Okay, okay. So three things basically, like dividing the context prompt, dividing the context, and providing the table description, and maybe like renaming the tables or something. You do, right?
Renaming the tables in our own schema is difficult, but instead, within the prompt, we are just mentioning,
Right.
hey, this table means so and so, and so use the table name XYZ that I gave, but what it actually means is this. So when you are joining, use this table name so that at the end, we still get the query that a
Mhm.
qualified SQL analyst would have gotten in the first case.
Yeah, yeah. I think yeah, table description solves that. Okay.
Yeah,
Thank you. Thank you, Arava, for answering my questions. And yeah,
yeah.
I think that was like I'm done with my set of questions. If anybody else have, they can proceed with theirs. Gajendra, Gagi.
Oh no, everything was quite clear, Sai. Thank you very much for the presentation and answering the questions. It was a great session.
Thanks, Sachin and Gajender, for hosting such an amazing speaking sessions.
Uh, Thank you for coming, Sai.
Thank you. Have a
Thank you.
great day.
Bye.
Bye.
Great, great. So we are just waiting for our next speaker to join in, and uh, as soon as she joins in, we would like to introduce her. She works at Uber as a senior engineering manager, right? And it would be wise to begin the intro once she's here. Meanwhile, Sachin, you have anything to tell our viewers? Right. Hi, Divya. Thank you for joining. Can you hear me?
Hey,
Yeah.
yes, I can hear you. Sorry about that. Somehow I'm unable to join from my laptop.
Right.
And
Yeah.
um,
So,
So
in that case, maybe we can just, you can just uh, talk about the session, your topic as is without presenting. I think that should be sufficient.
sure, I hope so.
Right,
We'll
right,
see about that.
right. Great, great. And for the viewers, I would just like to introduce Divya Rai, our next speaker. She has been spearheading technology initiatives in MNCs such as Credit Suisse, Citi, and Uber for over 20 years. As an experienced technologist, Divya has demonstrated expertise across fintech, logistics, supply chain, and product technology. With a strong professional background in requirement analysis, agile methodologies, and software development lifecycle, and designing highly scalable systems, Divya is a leader in her field. Please join me in welcoming our esteemed speaker, Divya. Divya, over to you. You are on mute, Divya. Sorry.
Sorry about that. Hello, everyone. Thanks for that introduction. Folks, besides what was just mentioned about my work, actually, my very very early career was into computer vision and AI, and back in 2004, I did work like in computer vision around collision detection and object recognition when Canon was trying to build hardware and software for the stream which is now very common, which is mixed reality and augmented reality. So that was like my very first taste of this field. But yes, my career took a path when I stepped away from it, and now with Uber, I'm again working in this field to some extent. So I'll start with a little bit around Uber and the scale of our data, just to give a perspective on, for example, number of customers that we have on a monthly basis. Just to give a high level idea around it is that total internet purchases in India in a month are roughly 100,000. And we are talking about these monthly customers which are on our platform, which is roughly 150 million today. Now, if we think about daily data that Uber processes, um, just to give that number into perspective, the entire data of Netflix, all the movies that they have on their storage, it's roughly 2 petabytes, slightly more than 2 petabytes. And the amount of data that Uber processes on a daily basis is actually 35 petabytes. So that's the kind of data that Uber churns. Obviously, we don't store all of that, and we don't keep it in raw format. It's in various compression formats. And now next is around the earners that are on our platform. And when we say earners, these are basically drivers and courier partners. Um, so when you think of earners, basically you think of top employers around the world. And I did a little bit of research before this meeting. And if you think of the Chinese army, that's basically 2 million. Indian army is 1.2 million. And if we think of corporate employers like TCS, that's 1.2 million as of today. And on our platform, there are roughly 7 million earners that we have. And this is obviously based on monthly data. And thinking about the queries that we have on our platforms on a daily basis, just to give perspective, folks who are aware of Indian market and apps like Swiggy, that's roughly 10,000 queries, give or take, on a daily basis. And on our platform, we have roughly 500,000 queries on a daily basis. And if we think about trips per day, um, giving you a ballpark number, this is roughly 28 million, which means that that's 20,000 trips per minute and roughly 300 trips per second. So since I joined roughly in that time, we have already probably taken 100,000 trips. So that's the context, just to give that perspective. And in Uber, we have something called Edge Gateway, which is basically the entry point of all of our apps, be it mobile or web. Um, all the requests that come through all of our apps, they actually go through that Edge Gateway, and that is actually designed to serve 100, close to 1 million QPS. So we get roughly million requests every second, and that's the scale that we are talking about. And I'm giving this perspective because when you try to design the ML models, there's this huge immense amount of data that is out there, and we have to look into every aspect, every dimension that we should be considering when we want to get the most out of these models. So that's a little bit about Uber scale. What I'm now going to talk about is some of our top problems. And if you have ever probably used Uber, you might have come across these problems while using the app as a rider. And some of the most common pain points are like, I can't get a ride. That's a very obvious one, right? The next one is like, hey, driver calls and asks for your location and where is your drop off, and then they basically cancel after that. Or the driver accepts the ride, but they don't move from their location. Or they cancel the ride and they say, hey, can you pay me in cash? So they ask you to cancel and ask you to pay in cash. Or this is a Bangalore problem. I think they don't turn on the AC. So these are like some of the very common pain points, and I'll talk about how we try to solve that through science and ML. So now I am not able to share my screen, unfortunately. Otherwise, I would have shown you like what were some of the experiences that we powered to actually solve that problem. The very first one is basically spinner time, wait time. And you must have seen when now recently, when you actually order a ride on the Uber app, you see an estimate of where exactly your request is. How much time is it going to take to basically give you basically connect you to a driver? And that kind of sets the expectation with the rider, and we realize that that experience is very positive. People usually want to know by what time they might be able to get the next ride. The next one was to how to improve the reliability. So this is another experiment that we did on our app, is that when you request a particular type of a product, and product means like Uber Go sedan or Uber X or Uber Black in some of the countries. And if we realize that the demand for that particular product is very high and there is less likelihood of you getting connected to a driver for that, we actually give a pop-up that, hey, if you want a faster pickup, there's this another type of product which is available, and this is the difference in your total ride cost, and do you want to switch? So we kind of give that prompt to the user to make that choice. And this is again based on a lot of historical data, hyper local data, and near real time data as well. And we'll talk a little bit more about that. The next one, another feature that we experimented with, when you all might have seen that option in your apps recently, is basically how can we pool our supply? So our supply is across different type of products. Like we have certain drivers who are available for just Go rides, certain are available for just sedan type of rides. So we have these different products, and all different drivers are basically aligned with a particular type of a product. And can we pool that supply together to actually enable a better user experience? So the one of the features that we rolled out was request any, and we piloted that in India. And now we are trying to experiment that globally, which means that we give you a price range, which is again based on a lot of heuristics and a lot of data that we collect uh, uh, week over week, month over month, and real time as well, that what could be the ballpark price of your ride based on the type of product that might get assigned to the ride itself. And the final was just a little bit of more user engagement. we realized that while you're waiting for your ride, if some fun facts about you or about Uber might be much more engaging. So you might have seen prompts like remember the first ride that you took with Uber in 2015, or how many trips you have taken so far since you started using Uber. So now going forward, I'll talk a little bit around, this was just an intro to the rest of my presentation, and we're going to talk about how has science actually driven mobility, and how we are using data and science to power a lot of these user experiences. So all of the ML work that we do, science is obviously behind it, and how science has driven ML at Uber. So in the current version of your app, you would see today that you get those 4 bars when you try to request a ride, and that the color of that bar progresses just to show how close you are to getting connected with a driver. So now we wanted to experiment a little bit with that. Can we give a counter, a timer, countdown timer to the user, and see how that goes? What's the experience like? And we pick a lot of data at the time of user experience. What's the impression, each screen impression time? How much are they dropping off at this moment when they're trying to request a ride? And that kind of helps us assess whether this experiment has been successful or not. So we started with countdown timer. The other one was that if we are not able to give you a ride with the very first estimate, can we give a second estimate? And that second estimate is going to be like a time range roughly, because and I'll talk a little bit about that later. So we kind of use the hyperlocal time, and then we also use time for a wider space range, just to give that second estimate, which might be much more closer to when you might get the ride uh, uh, connected. And the final experiment that we did was around wait time. So how much time do you have to wait until you get so it's a timestamp instead of a countdown timer. So it kind of gives you an exact time by when we can promise to get you a ride. And we did these experiments in different regions and collected data, and we're still working on that, and then we'll come up with which is the most optimized model that would work in a given market. And a lot of these experiments are very location specific. So this specific model that actually powered this user experience, it took a lot of features into consideration by for giving that prediction. Some of the features that we used for this was eyeball ETA, and this eyeball ETA, we'll talk about it later as well. Eyeball ETA is nothing but when you use an Uber app and you see different products, and it gives you the minutes that it will take for a driver to actually come and pick you up. So that's what we call an eyeball ETA. What's the supply availability? And this is something that we actually continuously calculate in real time. So a lot of our metrics, and that's where actually my team works very closely, is that a lot of our models are based on metrics, and these metrics are actually continuously calculated in real time, and that's our metric platform, and one of my engineering team works on that, and some other trip characteristics as well. So the challenge with this model was that the output has to be in seconds. So we want to give prediction something in seconds, because we know that anything more than that is the writers are going to drop off the app. So we want to have the prediction in seconds. The next is we want to minimize, and this is the bigger challenge, we want to minimize under prediction, because we realize that whenever we under predict, that means it's taking us longer to book a ride than what we predicted. That's a bad rider experience. And we see a lot of drop-offs when that happens. So you book a ride and it shows you, hey, you'll get the ride in 1 minute, and that 1 minute has passed. Maybe you'll stay around for a few more seconds. Most likely you'll drop off and you'll probably try another app. So that's where we want to minimize our underprediction. And obviously, the estimate that we give has to be within an acceptable range. So over prediction by too much is also not good, because if I say that you're going to get a ride in 10 minutes, most likely you'll drop off. You'll be saying, hey, I need a ride right now. I cannot wait for 10 minutes. So some of the model inputs, and this is obviously representative and not comprehensive. So the spinner time is one, which is the historical spinner time. Essentially, within your hyperlocal region, usually what has been the average amount of time that it takes for a ride to be connected. The next one is actually real-time data that I talked about, which is driver acceptance rate. So what is the current acceptance rate of drivers in that hyperlocal area? Like, out of 100 rides that we are offering to our drivers, how many of them are getting actually accepted? And that gives us an estimate of what is going to be that, how is that going to impact our predicted time? And then some historical spinner time for a much wider range. So how we usually do is that we'll first send an offer to the nearest drivers which are around you, and then we slowly increase the radius. So which is where we need to know the spinner time for the larger area as well. And the eyeball ETA that I just mentioned, and then our available supply. What's the current available supply? And this is a very, very big problem, how to identify the available supply. And available supply can take into account, for instance, the driver is probably near you and is about to complete a trip. So right now they are not available, but they will become available in maybe a few minutes. So we need to account them also as part of that available supply. And this model is like a 2-layer model. The very first layer is basically a tree-based regression model, and we use loss function to provide more accurate estimates. And the second layer is basically we do adjustment to just have a little conservative estimate. So whatever this model is going to return, we are going to add some more adjustment on top of it. Giving you just an example, maybe at few more seconds, just to give that conservative estimate. As I said, that under prediction is actually a bad user experience. So that's a little bit on how we power that user experience. The next is on how actually science drives qualitative insights. And this is where recently, at least this is a feature that we rolled out maybe a year back. And hopefully you, in the last 1 year or so, you must have definitely seen less driver cancellation. And this was based on a lot of feedback that we collected from our earners, that why are you basically not accepting the ride, or you're canceling the ride? And based on that, what we did was we started giving more information to our earners on the app itself. So you must have, if you have been in an Uber and if you've seen the screen of the driver's app, you would see that they get these offer cards popped on their screen, which gives them as much information as possible. And based on that, they can make an informed decision. So there are less cancellations because they exactly know what type of ride they are getting. Like, is it an Uber Go or Uber Sedan? Because each driver is actually, they can sign up for multiple types of rides based on their car type. And what is the mode of payment? And this is very important because a lot of time they're more interested if it's a cash payment. So we tell them upfront whether it's going to be a cash payment or an online payment, what is the rough amount they're going to earn on this ride. And we also tell them if it's a surge price. And this is important because they know that they're probably earning more than what they would have for this particular trip. And also how far away is the pickup location and how far is the drop off. So they can do that estimate that are they making enough for the trip that they have to take. So based on all this information, and this was this was done through a lot of feedback and experimentation, and we realized that this has helped us reduce a lot of driver-initiated cancellations. The next one, I'll talk about how science drives experiments, and I'll give you a bit of an idea that at any given point, we have close to 50,000 experiments that are live. And a lot of that is powered through what our data science team does. So we realize that we try to improve our supply, and we do that by onboarding as many earners as possible. But the new earners, we saw that they do get onboarded, but the time that it takes them to start with their first trip, that life cycle is very long, and how we can actually improve that. So we started doing these checklists for these new earners. So when they onboard onto our platform, they actually see a kind of a checklist like go online or go online at peak time, take your first trip, and they can actually do all those steps, and it strikes out, and they get this celebratory message in the end. And after that, they can take their first trip. We give all these insights to our drivers to make that informed decision. So, for example, go online at peak time. When that shows up, we actually show them based on all of the data analysis and insights that we have, that what are the top peak times in the region where they are operating. And they can actually go online at around that time to ensure that they have faster trip conversions. And once they complete all these steps, we have realized that actually that has been a very positive experience. And we have actually continued to have these earners on our platform take more trips, as opposed to initially either they would just on board, and it would take them months to actually be part of that active supply of drivers that we want on our platform. So I'll skip through a few slides because you folks cannot see my screen. The next one I'll talk about around how the science has driven some of our product features. And around that, we did a lot of analysis around our rider data. So this is very, very interesting, and I'm sure you folks must have done the same thing, that you try to book a ride and it's taking you forever to actually get connected with a driver. You cancel it, and then you re-request a ride, maybe with a different type of maybe you'll pick an Uber Auto or Uber X, depending on where you are, with the possibility of that maybe you'll get that particular ride connected much faster. So when we did that, we did this analysis at a global level, and we saw that there are 15% rider initiated cancellations, and out of that 15%, 55% are actually re-requests. So 55% of the folks that cancel, they will actually re-request. And out of that, 30% are actually going to request a different product. So this kind of funnel, when we did the analysis, we actually realized that people are just trying to hack the reliability and availability of rides on Uber app. And this is, by the way, consistent globally. So when we started doing this analysis across all of our markets, we saw obviously this was consistent, but then there were these specific outliers. Like in APAC, Delhi NCR had one of the highest instances of this behavior. In EMEA, Cape Town was the next one with 54% re-requests. In LATAM, Bogota was close with 47%. And in US and Canada, LA is at 50%. So it's not very specific to a particular market. It's actually consistent globally. So that's where we came up with the request any feature, which I just talked about initially. And that feature was actually powered through the work that was done by the data science team on collecting what the user behavior is and how we can actually automate that and give that behavior upfront to the user to use directly on the app. So when you use the app, you will see the request any option, and you get the fare range, which means that depending on the products that are part of the bundle, which is basically, whether it's going to include Go, Sedan, or Premier, based on that, we give you the price range. And then the final price is going to be dependent on which driver actually accepted the ride. And this particular experience actually was a game changer. We did this as a tryout experiment, and we saw immense improvement in and reduction in rider cancellations. The other thing that we experiment with this particular feature was that how can we use our request blocker entry point? So request blocker entry point is essentially you must, if you've had probably online payment, what we do is that once you complete the ride, and if you have an online payment, the ride will get completed with no issues whatsoever. But if that online payment is basically through a credit card, the next time you try to book a ride, it will actually block you from doing that and ask you to pay for your previous ride. And we used that prompt actually for this to power this experience as well. So the moment somebody is trying to book a ride and we see that that particular trip is actually going to take them much longer, we block that request and give them a prompt that, hey, if you are in a hurry, why don't you request any? And then we will be able to give you a ride within these seconds. And this overall experiment we initiated with India, and now we are expanding it globally because of the success through that current experiment. We also use science to drive optimizations, and I don't know how many of you are aware of Uber shuttles. This is something that we again experimented in India within very specific markets, and it basically is a network of shuttles or buses which operate on fixed routes, and they run on specific schedules. So just some food for thought over here. And I'm not going to go into like the specifics of how we actually solve that. But just, suppose if you had to create a network of these shuttles or buses, what are some of the key questions that you need to answer? One is that, where will you send these thousands of buses? What are the specific routes that they should operate on? Where should they start and where should they end? What should be the stops on that particular route? At what time should they start, or what should be the schedule of these buses? What would be a rough ETA or travel time of that on that particular route? Because we give all of that information to the rider who's trying to book a shuttle ride on our platform. And what should really be the price for it? Because it really depends on the volume. It's very, very different from how Uber rides, the usual rides they work. So over here, the pricing of the ticket is going to be very different from how we actually calculate our prices for the other rides. How much should we pay our suppliers? Because these shuttles are not owned by Uber. These are other third-party fleet partners that provide the shuttles. So we need to pay the suppliers as well. So how much should we be paying them? Should it be based on utilization? Should it be straightforward payout? What should be that model to optimize Uber's earning? How do we identify the demand? Because for our usual rides, we actually have immense amount of data to figure out what is going to be a demand at a particular time. But in the case of shuttles, we actually don't have that data, at least until the point when we started working on this problem. And we identify these users to be using these shuttle services for commute, so which means that they're going to be repeat users, and they're probably going to use twice every day? And should there be a subscription or a membership model? And what should that really look like? What should there be a discount, and what that effective discount is going to be? And how should we even utilize our bus capacity? What should be the usual shuttle size? Uh, how can you uh, keep the utilization of these shuttles optimum? Should it be overutilized, underutilized? What would be that fine spot where we give the best experience to our riders as well as our shuttle operators? So just some food for thought, and all of these questions actually we answered through a lot of analysis that we did through our own internal data, as well as we took data from our external vendors as well. And the next one is about how science actually drives insights for customers. So we also give a lot of insights to our customers, and over here, customers are both riders as well as earners. For us, earners are also equivalent to customers. So the very first one was that, as I mentioned, that for the first time drivers, we actually show them a heat map, which gives them the areas where right now there's a surge, and which means that they have higher earning opportunities in those areas. So the moment they are about to go online on their app, the region where they are, we show them that show that map as a heat map. And we also tell them whether right now if they are in a busy area, so they don't really need to go anywhere. They're already in the middle of the hotspot, and they can choose to actually go online right away. And if they don't want to go online right now, but they know that somewhere in their city or the area they're operating, there are hotspots and surge areas, they can actually select the option of to navigate them to the high earning area. And we actually pick the highest earning point for them and create a route that will navigate them to that point where they can actually get those surge rides that they're looking for. So these kind of insights have really helped our earners to make the most on our platform, and that helps us to maintain our supply on the platform as well, because the more information that we can give to them, which is going to increase their earning opportunities, the more likely it is that these drivers are going to stay on our platform. And the next one was around how we can give more insights to riders. And I mentioned a little bit about this in the very beginning, where we give them eyeball ETA. And the eyeball ETA is like, for all of the products, we tell you how much time is it going to take for that particular product, for that particular ride to come and pick you up. And we also now tell you which is the recommended one. So for instance, if there's a similar ETA for Uber X and Uber Black, which one do we recommend? Because based on our acceptance rate, based on the overall supply right now that we have, how highly likely it is that actually we will be able to provide you with a ride of that type. So these kind of insights we provide to our riders to make an informed decision. And the last one, I hope I am on time. The last one is around how we actually drive a lot of internal efficiency as well. So um, some of you might know, but we do a lot of our own internal tooling to improve our developer productivity. So we do a lot of analysis on, for example, where our engineers are spending most of their time and can we optimize that? And we do a lot of that through science. So one of the things that we did very recently was on automating root cause analysis. And root cause analysis, if any of you is familiar with the on-call rosters. So our engineers are actually on call to make sure that if there is an issue, they are there to take care of it. And we realized that they actually spend a lot of time in doing that root cause analysis. So just to give you a perspective, we have roughly 5,000 engineers and we have 5,000 microservices as well and counting. So we roughly have one microservice per engineer. And if an engineer is a part of a team which owns 15 microservices, during their on-call, they're actually supporting those 15 microservices, making sure that they are available, they are up and running, they have very low error rates and latencies. But in case of an incident, and when we see an incident, basically, suppose there's an outage, one of the core services just stopped functioning and came down. The engineers spend a lot of time to figure out actually which service caused it. The final impacted service might be not the one that has caused that outage. That problem might be somewhere else, and that actually takes a lot of time. And before we can even mitigate that, the more time we take to mitigate that outage or that incident, Uber loses money. So it's very, very important on how we can quickly do that root cause analysis and mitigate that issue. So what we did over here was the moment an incident is created, so we have an internal tool where you can actually create an incident that, hey, this particular we have an issue with this particular service or this system. And as part of that, we mention what are some of the impacted services in that incident. Now, from those list of services, we actually use our dependency graph of all of the services that that might be causing the outage of this particular service. So we use the entire lineage, the call graph of APIs, and try to figure out what are the list of services that are part of this incident. And we use a lot of information which is available at that moment. For example, error rate, latency, what is the historic and live data. And we try to then further do anomaly detection using Z-score. So based on all of this data, we try to figure out, hey, where is the anomaly in all of the information that is available. Based on those anomalies, we pick the top 5 potential root cause services. So until now, we are still not sure, but at least we have reduced the impact radius and analysis radius for the team. So for these top 5 services, then we gather actually all of the logs for these services, and we are talking about a huge amount of data. Then we further do aggregation of these logs. So, for instance, if the same kind of log is happening every second at a particular frequency, we try to aggregate and show the trend of each one of those logs, and that kind of represents that if that trend kind of aligns with when the incident started, that particular service might be the root causing service. And then we use Gen AI to basically summarize and give that information upfront to the engineer who might be working on it. So they can actually do the analysis and mitigation much, much faster than what they were probably doing before. So I'll end with that. And I hope this was informational, but just to give a summary, we kind of literally do a lot of analysis, not only for our external features, but a lot of our internal tooling as well. Thanks, everyone.
Thanks. That was a great talk, Divya, and like it was very informative. I would request you to send the presentations. I believe that it was very well prepared, which you couldn't share here. So I would like to read that out. And the curiosity, it's like whenever I book a cab in Bangalore, so it comes to my mind that how exactly it is happening. I remember that other than Uber, I hardly use any other platform for cab booking because of the support they provide. Because of the support they provide. So I think the best among all of the apps, like whether they are like food delivery apps or maybe these mobility apps like Uber, Ola, etc. Uber has the best support. Like whenever I raise a ticket, I get the response. So how exactly, like I have a question on the support, that how exactly you reduce the support time, and see the support could either be from a driver or could either be from a rider, right? So is like how exactly you're incorporating AI to reduce the support time, or give the best responses to the users. I once talked with a rider, oh sorry, a driver also in a cab, and he told me that other than Uber, nobody else listens to their query much. So I would like to.
That's that's actually great to hear, first of all. And we actually as you pointed out, we actually use a lot of AI for that. So essentially, what we try to do is we capture historically all the queries that have come so far, and how our support agents have actually resolved those. And we use that, and along with that, a lot of new features that we roll out. So most of the time, the issues that are raised by be a driver or a rider, it's most likely because some experiment got rolled out, and we actually uh, maybe that experiment did not come across as it was intended to. So we try to give a lot of that information upfront to our support agents, and we have a very comprehensive internal tooling where they can actually enter the query that they get from our riders or drivers. And based on that query, we upfront try to tell them what could be the possible resolution or what could be the cause of that query. So, for instance, um, a writer asked the question, hey, I was incorrectly uh, charged this much amount. It should have been charged this much. And when they enter that query into our system, based on the driver information or the rider or the eater information that they provide, we actually try to assess, first of all, what was the last order or trip that they took, and then what was there an experiment alive on that particular user or not, and could that experiment have actually led to this issue. And then if we are not able to assess get any information on any of those, then we actually use the past resolution to actually quickly give a resolution option to our support agents so that they can take those actions very, very quickly. And we are continuously evolving and changing that, because that keeps changing based on our product, and our product continuously evolves as well. So we need to provide that active information very quickly to support agents, because they are usually not aware of what new features rolled out. They just get the query right away.
So I believe like it's more of the automated information, like already compiled information the support agents get, so they are able to give the support much earlier.
Yeah.
Okay. Other thing is that as you explained that I remember like Uber driver used to ask this, like where do you want to go, the drop location. But now we have like Uber have changed that, and I think most of the rides the driver already know that where I'm actually going, right? So, do you think that that leads to a cancellation, right? Like, let's say if I'm there in front of the driver and I'm able to convince the driver that, okay, please drop me to that location. Or maybe if, let's say, the driver figure out that, oh, the guy is with the family, and like there's this emotional thing, right? But on the app, it is very convenient to just tap and cancel the ride. So do you think like those kind of requests that leads to more cancellation?
That's a very good question, and actually, the we give the as I mentioned, that we actually show the offer card to the driver, and we don't actually. So we, even in that space, we have done a lot of experiments, and one is like sequential driver offers. Sequential driver offers is, for example, when you request a ride, it's going to go to one driver. If that driver does not accept that request in, for example, 10 or 15 seconds, we have a timer on that, it will go to the next nearest driver. uh, the other way of doing it is we actually do a trip radar. Trip radar means that we actually send requests simultaneously to like 10 drivers. And whoever accepts the ride first, we assign them. But to your point, all of the information is upfront given to them. So once they accept, they are accepting that based on the information that is available upfront. So they already know how much they're going to make, where is the drop off. And if they're aware of the traffic pattern, most likely they will not accept it because they know that, hey, on that route, I'm going to hit a lot of traffic. And this money that I'm going to make is probably not enough. So that's where you will probably maybe will it you the rider will have to wait probably a slightly longer to get a ride, but once the driver accepts, that actually cancellation after acceptance is very, very low after this experiment.
Got it. But so rejections might increase, but the cancellations will reduce drastically.
Yes.
Okay. Right. So another question from user, I'll just read it out loud to you, is that uh, hmm. So all of these features, right? Like I get the point that data is there, but how does like AI helps in it? Like deciding that, okay, we have to show that information upfront, or let's say like payment gateway, right? All of these things we have to show upfront, or maybe the time or to get the or to predict the like what where when exactly I'll get a ride. So how does like the AI implementation work in this?
So we actually do a lot of experimentation, which is again powered by science and ML models. So, for example, data science is going to analyze a lot of data, and they try to evaluate the data on various dimensions and different granularities, and they come up with some behavioral patterns that they have seen based on the data. That, hey, if the rides are high price rides, we see that there are lesser number of cancellations by the driver. Or if in some cases, and this is very interesting information that we found was especially around Uber Auto that we launched in India, that there is higher rejection on very small trips. So when we see the data at 1 or 2 kilometer range, we see that Uber Auto probably will does not accept because it's just too low of a price for them. And then they also don't accept when the ride size is the length of the ride is very, very high, like maybe 10-15 kilometers. There's a sweet spot somewhere in between where we have very high acceptance rate among the drivers. So the data science does a lot of analysis and come up with behavioral patterns. Now, on those behavioral patterns, we actually will come up with a model, and then we will have multiple models, and those multiple models we run on different experiments. So for any given feature, we would have probably 4 or 5 experiments that would be live at any given point, and we try to have a control group and a group that has been that has that experiment alive. So we do a lot of analysis within that control group and the treated group of that experiment. And then again, data science will go back that, hey, based on that behavioral pattern, when we suggested this, what was the final outcome? Then we further refine the model based on the data science evaluation of that experiment. So we'll further fine tune. For example, the experiment is working fine, but maybe our price range is not correct, either for the driver or the rider. So we'll again fine tune that experiment, and then we'll again roll it out. We continuously run these experiments, and sometimes these experiments run for months before we can actually say, okay, now we have really figured out this feature, and we should roll it out globally across all our users.
Great. That's a good insight. So one last question is that even though Uber is from like outside India, and there are already a lot of companies who are accommodating this market, the cab market, still the Uber I think is able to cover the maximum amount of users and the riders. And like what exactly like from the tech point of view, what exactly Uber changed while they launched in India, or like what what different they are doing while accommodating India?
So one of the things, and I'll talk a little bit around, airports, because Indian airports are very different from all of the other airports. And actually, airports is a very interesting problem that we solve. So if you go to an airport at New York, your experience as a rider is going to be very different than if you go to an airport in India. And even within India also, a Bangalore airport experience is going to be different than an airport, for example, in Pune or Hyderabad. So we actually try to do a lot of analysis on how these different markets operate. And for example, in India, we actually also started analyzing our supply and demand. And supply at airports is very, very different. So for instance, Bangalore airport, take for instance, it's like all the way outside the city. So your supply of drivers is very, very limited. But how do you ensure that you get enough drivers at the airport at a given time based on the demand that you're predicting? So we know that, and we get that data that how many flights are going to probably land at a given point, and what's our usual conversion ratio on those flight passengers. And that means how many drivers we should have at an airport. And these drivers are actually not really actively available in the queue. They're actually in some parking lot. So we actually send them prompts to go to an airport at a given point, because the possibility of them getting a high ticket price is much higher. So figuring out these kind of special problems, we use a lot of data, and a lot of ML as well is involved over here on how do you figure out what's the current supply, and if are we undersupplied. If we are undersupplied, how can we get the right supply to the airport? Who are the drivers that we should be targeting to prompt them to go to the airport? And the other one is like, how can we use some of our other products to make that supply available? For example, reserve. And most of the time, folks use reserve for an airport drop off. Can I use that supply to be pulled into our airport supply for airport pickups? So this way, we first try to handle that for an airport like Bangalore, which is totally outside the main city, and then we kind of extended that model for other locations as well.
Great, great. Never realized, never thought of it that way, that Uber is analyzing the flight data as well. I always thought it that way, that the number of rides, like people going to booking for to the airport and from the airport. Anyways, thank you, Divya. Thank you for answering all of my questions and answering the curiosity as well. Okay. That was it. Sorry.
No, I was like happy to answer.
So I'm done with my set of questions. Like if anybody else like Gajendra or Gargi or Sandeep also joined. So
Excuse me.
Yeah, I've been listening. So yeah, this amazing answers by Divya. And yeah, I don't have much answers, much questions. Most of these are already answered. And is there anything from the YouTube channel or others?
I checked, and I basically okay. So there is one question. It says COTA, Customer Obsession Ticketing Assistant works. Can you give some insights on that? How this works?
What do we want to know about that? Because that can take an entire presentation.
Yeah. So I think that is the answer to that. We might or Amit. This question is from Amit, so I would say that Amit, you can drop this question, and we might get it resolved over an email or something. Right. That would be a better approach.
Okay. You can just briefly summarize the thing, in a paragraph, and that should be good enough for it. Yeah.
Excuse me.
Okay. So,
Excuse me, I have a bad throat.
I think you can take a break. Is it up? The time is up, or
yeah, I think we are about the time, Gajendra.
Yeah, thank you, Divya, for the wonderful session. And I think it's time to call our next speaker, right? Uh, Mr. Arpit Goliya. I'll just give a brief introduction about him. Uh,
thank you, Divya. Thank you so much, and it was so insightful to us. And yeah,
Yeah, it
yeah,
was a pleasure, but unfortunately, I wanted to share my presentation, but yeah, it didn't work out. I'm on my work laptop and it was just not letting me log in.
yeah, that's okay. That's okay. I think that was it. All right.
Thank you, Divya. All right, for our next speaker, Arpit Goliya, I'll just give a little bit introduction about him. So Arpit is a results-driven CTO and CPO, Chief Product Officer consultant with over 16 years of experience. He's been guiding businesses towards success in the landscape, and Arpit excels in envisioning, advising, and delivering innovative solutions that align with both businesses and technical needs. Currently, Arpit leads technology and business strategy teams comprising of over 250 plus professionals. He's also an enthusiastic supporter of early stage investments in startups, particularly in sustainable fashion, clean energy, people tech, Web3, media tech, legal tech, and ed tech. So quite a lot of industries that Arpit is involved with. Please join me in welcoming our esteemed speaker, Arpit Goliya. Thank you.
Thank you so much, Gajendra. Glad to be here, everyone. And I think I have to speak about robust AI. So maybe we can start, Gajendra, because can you give me the screen share? I'll just share the presentation.
Yes, I think everybody has the permission to share.
Okay, sure. So great. Let me know when you all can see it.
Yes, we can see it.
All right. So everyone will cover this particular agenda today, right? So before I talk about robust AI, I really want to touch a few stories around what have been the recent AI failures, right? And why is robust AI that important? And so we will go through some of the AI failures first, and then we will also try to understand what it takes to take an AI to production, right? So there might be a lot of people doing a lot of things as AI projects, but the production grade AI is slightly different, and that is where the robust AI comes in. And at what point robust AI fits in? What are the key considerations? What are the different systems? How do you measure robustness of an AI system, right? And then probably for the next 5 minutes or so, I can take a couple of questions. So moving ahead, so these are some of the failures which have really happened, right? So for example, Air Canada, they had to pay a customer for their chatbot goof up, right? So what happened was that they had a virtual assistant, and the virtual assistant gave the information that you can book bereavement tickets and take the refund later, right? But the airport policy was not that. So the data that the chatbot has given to the user who was chatting to the user was the incorrect information. So ultimately, it went to legal battle, and the customer had to be paid. So there is another company called Zillow, which had to write down entire 304 million in inventory in 2021 because their ML algorithm actually made them purchase prices at houses at a higher price, right? So these are a couple of failures, and there have been many such failures overall across the industry, which people have seen. And the reason is because you have put a system into production that is not that robust. It has not been tested properly. There are a lot of other considerations which have not been taken. So robust AI is a trend where more and more companies are trying to understand how they can ensure that the models that they put in production uh, actually are resilient models and are able to sustain long time with the data variations and other items, right? So when we talk about a production grade AI, right? So if you see a typical AI project would be like a very small part. You can take some data, you can create a model, and you can do some things with it. But if you really want to productionize it and put it into production, uh, then it requires a lot of other things, right? So a small recommendation engine, but when you want to put in production, there are a lot of other variants, right? So for example, you might have trained on a small set of data, but now in production, you're getting different data. Or it could be that you had very limited data, right, at the very start, and you were not able to train the project properly, but you cannot go with that model onto your production. It will not work in the production at all, right? And some of the examples that are there is, right, so for example, everybody has seen a lot of research around, you can diagnose diseases from X-ray, right? And people talk about that machine learning has predicted so and so disease from photos. But why are those systems not live at large scale, right? So if the system is available, if AI is really able to diagnose from a photograph or an X-ray, why are all the hospitals not using it, right? Because that achievement that has happened probably was done at top hospitals where the instruments were latest, where the image quality was latest, right? But not every hospital will have that kind of an environment. So the AI which has been successful with a limited set of data or in a limited environment might not really work at other places, right? And that is why you don't see these systems deployed at large scale across the board. Similarly, there was a case where there was a manufacturing company that did a project, for visual inspection on the quality, right? So you have a production pipeline where your items are getting produced. There is a camera there on the top. It takes the photo, and then it is able to tell you whether the quality is good or not, right? The production deployment was done, but then there was a lighting change, and that impacted the results, right? Slowly, what started happening was the result started going down. So there are many such things that you have to really take care of when you talk about, how you want to put your model into actual production, right? And these are some of the things, right? So, for example, when you talk about a small AI thing, you might be doing a proof of concept and doing exploration. But when you really want to put that model into production, you have to talk about the pipelines, CI/CD, the reliability, scalability. If that model is being used by many people, how will it perform? Whether there will be latency or not, right? If there is unknown data, new data which has come in, how will the model perform, right? A lot of experimentation that is done at the machine learning is in the controlled and ideal conditions, right? But the real world has got dynamic environment. So you need to prepare your machine learning model to handle those cases also. And when you're evaluating the machine learning model, when you're doing it with the limited data, you're focusing on accuracy and speed. But when we want to go at the production level, the reliability is more important than accuracy, right? So if your model, even if your model is 99%, 100% correct, and in production, there are cases where it will give you false results or wrong results, it cannot be deployed, right? There are some mission critical production things where even 1% of the false case is not good enough, right? So this is another consideration, that whether your model, how can you ensure that your model will always give reliable results given the same inputs, right? And when you go to production at a large scale, how will you ensure that you are able to run the inferences in the model in a limited cost, right? It is not that your model is taking a lot of money to run. And then the next part is infrastructure, right? So when we talk about AI projects versus production grade AI, again, when you're doing small scale experiments, it is fine. You can do on smaller machines. But when you are production ready, you have to think about load balancing. You have to think about as more and more requests will come, how will it scale? How will you loop in the feedback and go back, right? And then there is a team also. So when you do a model, initial modeling is done. Maybe the data scientists and researchers are good enough, right? But when you want to deploy it, you will have engineers also. They would be writing the APIs, exposing the model through that API. Your data scientists will also be there to monitor and see if any improvements are needed. And then there will be entire DevOps pipeline, right? So this is the overall difference between when you do a smaller AI project versus a real production grade. And it's very difficult to have robust AI models, as we saw the failures. Bigger companies like Air Canada, Zillow, and many other companies, their models do not perform that well when they go to production, right? So what is the solution of that? How can you ensure that your AI model will perform well? And that is where your robust AI comes into picture, right? So when we say that we are creating a robust AI system, what does that mean? So that really mean that the system will have these 4 core attributes, right? One is the system will be resilient, which means that if there is any failure, of if you have given some data which was not given at the training time, it's a new scenario, new data, the system will not crash. The system will still perform. It's reliable, which means that consistently there is correct output which is coming, right? It's adaptable, which means that you are sharing new data. So for example, your model could have been trained, if it's a voice model, let's say, and if you're trained the voice model on adult voices or children voices, and the application has gone live, but now more and more female users are using your application, and they are using the application to through their voice. Now, this is a new data which is coming in, which might not have been there at the time of training, right? So will your model adapt to this? Or will your model will not be able to give any results when this new data is coming in? And then the last and the most important part is security, right? As in when you create models, people will try to hack into those models, as we have seen with a lot of LLMs and other things which have been happening. People will try to put in some information and try to extract information from the model, or try to deviate your model in a way that it starts giving wrong answers, right? And which is where protection against adversarial attacks, right, and data breaches come in. So if you're thinking about all these things, then actually you are creating a robust AI, right? So not just creating a model, training on the data, and just getting some sort of an accuracy, right? More than that is required to build a robust AI system. And these are some of the core attributes. Then you also have some additional attributes. And today everybody talks about responsible AI, ethical AI, right? So if you add some more elements to what we had discussed about the robust AI, then you will get a responsible AI, right? And these are those elements that your AI model should be explainable, right? Which means that you should be able to clearly tell why the AI model is giving the output it is giving, right? And if you consider the healthcare domain, it becomes very important, right? So let's say if you're using a model for some diagnosis, and the AI model is not able to tell the rules or the symptoms. Okay, I saw this symptom, and that is why I'm recommending this diagnosis, right? Until unless that transparency is there, it will be very difficult for that model to get adopted, right? So explainability is an important criteria. Fair is important criteria, and this is where your training data mismatch comes in, right? So if your training data is not diversified, then it might result in the algorithm getting biased. And we have seen that in a number of cases, especially in the recruitment platforms, where you would see, if you research, you would figure out that there have been some deployments where they would reject candidates above 60 years, or they would reject candidates of a specific race or a specific color, right? And why is this happening? Nobody has done this deliberately. It is because that is how the training data was. The sample set that they got for the training data was skewed in favor of some specific data elements. And that is why the algorithm is getting biased, right? And it's a known problem. So if you see that data is like that, then you need to diversify your data, right? And either generate your data yourself for the other attributes, or use other sources to generate that data to ensure that your algorithm is fair. And then your algorithm should also be verifiable, which means that if there is an output coming, you should be able to clearly tell that, this is what was intended, right? It could not be an output which you cannot really verify that if I, always give these set of inputs, am I getting these set of outputs or not? Or maybe a range, or maybe a probability. depending on what kind of model you are building, right? And then it should be efficient, right? Because if your model is very accurate, doing good results, but then it requires hundreds of GPUs to run, then again you cannot really productionize it, right? Because that amount of money spent will not give any business ROI. So these are some of the attributes in terms of robust AI. And now where does robust AI fits in, right? So when you talk about machine learning, right, and if you see how these systems are built, right, so you would have some sources of data. Either the data would be coming from sensors or other ways, which will be structured data, or social media or some other tags, which will be unstructured data, right? And this is where you would do some sort of a data management, data curation, labeling, clean up the data, make sure your data is prepared for fair results. There is no skewness, there is no a bias towards a particular set of data just because you have that more in your training set, right? And then you will apply some sort of machine learning algorithm to create a model to extract that information and translate into knowledge. It could be a supervised, unsupervised, transfer, learning, reinforcement learning, or nowadays generative AI have a lot of other models, right? And then that models will ultimately create some course of action between humans and machines, right? And finally will given some results. And all of that is happening in terms of some computing, right? So GPUs are what is being used now. These are upcoming neuromorphic and quantum computing, right? But at all these layers, you have to understand whether you are building a robust AI system or not, right? So at every layer, at data conditioning layer, at your algorithm layer, at your interaction with the human layer, you have to really go and understand whether your AI model takes care of these features or not, whether it is explainable. You are tracking the matrices, you are doing the bias assessment, you are verifying your results, you are ensuring that your model can be validated. Then you are also ensuring that there is a security in place in terms of the standard security practices also, but also in terms of robust AI practices, that nobody can give you a data which will, make your model go haywire, right? And then you have your policy, ethics, and safety, which really varies from companies to companies and how they want to adapt it. But robust AI, if you really want to create a production-ready, production-grade system, all these elements have to be taken care of at each stage. You cannot really say that we will take care of it later, right? As you are building, even when you are not building your model, right? You are just working on your data, which is like 70 to 80% of your initial work. There also you have to understand whether your data is skewed or not, right? What kind of algorithm will fit in properly? Will this algorithm, based on the error rates and other things that we will see, is able to give you right results, verifiable results or not? So some of the key considerations at different stages, as we talked about. So when you talk about data, you have to really ensure that the data quality is good. It is free from bias, right? And then if there is any sensitive data, you are ensuring it cannot go in output, right? So let's say you're training a data where there are some phone numbers, somehow it came in, right? Now your model cannot split that data because that is private sensitive data, right? So that kind of understanding should be there when you're designing the system. Data security in the sense that I should be able to access only the data which is limited to my query, right? And not anything else. And data governance, which is basically an org level policy, like which user role, what kind of queries will be accessing what kind of data and all that, right? So one of the things that we see a lot of times with generative AI as of now is people have doubt. If I put something in ChatGPT, will it use that and spit it out at some other place, right? And that is why more and more organizations, they want to have private LLMs. They want to ensure that their data remains in their control, right? So that is the part of data governance. So first part is data. Then after your data is cleaned up, you have thought through your data in terms of robust AI. Then comes your model development, right? Where your model selection becomes very important if you are selecting the right algorithm or not, right? Because if that is not the case, you might get good results in your training time, but when it goes to production, over a period of time, your performance might degrade, right? and then how you are training your model, right, for accuracy and efficiency, whether you have enough data diversification or not to handle anything that will come in future, right? And then how are you evaluating your models, right? Whether your evaluation parameters are considering robust AI or not, right? And there are a lot of parameters through which we can measure the robustness of an AI model. So ideally, you are taking care of that or not, or you're only focusing on accuracy, right? And then how are you deploying your model into the production system? Once it is deployed, how are you monitoring it, right? And then how are you taking the feedback to ensure that your model is continuously improved? So we covered the data layer, we covered the model layer, right? So now comes the ethics part, right? It is known. The algorithm bias is a known problem. Everybody knows if your data is skewed, your algorithm will get biased, right? So are you doing something about that or not? So when you study your data, are you trying to figure out whether this data is biased or not? And if you have figured out that the data is biased, what are you doing to augment that data so that that bias goes away, right? And then the question of fairness, right? Whether your model will give equitable outcomes for all users, or they will prefer a set of users, right? So if I, as a software engineer, is asking for something and the model is giving me some different answer versus, let's say, there is a carpenter that is asking something to the model and the model is giving some different answer, right? So is there fairness in the system or not? And then whatever the answers are coming, are you able to explain those decisions, right? Is it a black box, total black box? Nobody understands. We just give some sort of inputs and some sort of output comes in and nobody can explain that output, or you can tell how the AI is making some decisions, right? Especially in systems which are critical. So if it is an AI software which will review your resume and reject your profile or select your profile, that software should be able to explain the decisions. Why was this resume selected? Why was this resume rejected, right? And then ultimately, as an organization who is building that AI model, you have to take the accountability and other to some ethical principles and guidelines, which might vary based on the organization needs. And then there are some technical needs, which is security, again, explainability, whether your model will scale or not when more and more people use it. And interoperability, this has become very important in the sense that, is your model really tied to a platform, right? So tomorrow, if you want to change your cloud, will you have to redo your model, right? Or you have exported your model in a format that it can work across different clouds, right? Or maybe different frameworks, right? Is your model such that it will only work in TensorFlow, it will not work in SageMaker, let's say, right? So how have you created your model? Sometimes this decision could be, yeah, that we don't want the model to be interoperable because that is how some other business use cases or business ROI is coming in. But again, this is a consideration. And then there is a business consideration. What is the return on investment? What is the cost benefit analysis? What are the risks associated with model? And we already saw the failure cases, right? A company had to pay 300 million, write-off 300 million because their model was, making them purchase home at right prices, or an airline had to pay a refund fee just because the model, the chatbot gave wrong information, right? And then managing that change, right? So when you are deploying the AI system, it will impact a lot of areas within the organization, outside also, in the way everyone works. So how are you handling it, right? So all these considerations, data considerations, model consideration, ethical consideration, technical consideration, business considerations, right? They go into building a robust AI system. If you see some of the use cases, so why is robust AI important? And now if we drill down to some of the use cases, right? So imagine you have an autonomous vehicle, right? And if your AI is not robust enough, it will simply result in accidents, right? Even now, after so much, of self-driving kilometer hours, sometimes we have seen that there is a flaw and the Tesla car breaks down, right? So it is very important that when you are designing a system, you take care of some of the key elements, right? So for example, in an autonomous vehicle, you will have redundancy, right? You cannot have one sensor not working or one camera not working, right? And then nothing you can do, right? So at the hardware level also, you will have redundancy. At the input level, you will have redundancy. You will run through a lot of simulations before you actually put something on the car, right? So a new patch cannot be really updated without a lot of testing. And if you come to healthcare, we discuss this, that you can either say that I'm not able to diagnose this, right, from this picture or from this photograph or from this X-ray. The AI can say that I'm not able to diagnose this, right? But it cannot make a false case. If the disease is not there and if the AI is saying that there is a disease or otherwise, right? That is what we need to avoid. So if you're developing a healthcare model, which is going to take an input and do some diagnosis, then this becomes very important criteria. Similarly, in financial trading, imagine you have not taken care of the robust criteria. One fine day, something odd happens, and your algorithm start misbehaving. Either it will sell what was not to be sold, or it will buy what was not to be bought, right? So again, having those considerations, thinking through the future, and ensuring that all those edge cases, all those things are taken care of when you're building the model, right? And if the model is being used for disaster response, then one of the important thing is, again, reliability, right? You cannot say in a disaster response that my model is 70% accurate, right? Or my model can give false positives also, right? So how can we do, right? So how do people solve these challenges? We have talked about challenges where the data could be biased, data is insufficient, where it could be the case that people are not able to or the hackers are able to game your model, right? So how do you take care of all those things when you're developing your model, right? So these are some of the potential approaches. So Ansible method is a very simple approach, which says that we will not rely on one model, right? We will use a combination of models, and that is what will result in the overall performance improvement, right? So in a lot of the cases when we define a machine learning algorithm, so for example, in image classification, you can actually combine two things together to get better results, right? So CNN at the image layer will help you identify features, right? And then SVM will help you classify the image, right? And that is how you will get better accuracy. And maybe some of the data biases and other things will also go away. Another part is adversarial training, where we give corrupt data intentionally, right? So because this is what the hackers are trying to do, right? So we will give wrong data to the algorithm, to the model. We will give corrupt data to the model, and we will see how the model is behaving, right? So for example, very simple case, right? If you're developing a facial recognition application, and it actually happened, right, when Apple launched the initial version, right? So your facial recognition is happening obviously through your facial features, but also through the depth of like where your nose is, where your eyes are, and a lot of other conclusions are there. But imagine somebody creates a 3D view or takes a 3D printout of your face. Will your facial recognition algorithm say it is a right match or not, right? So now that is adversarial testing. So you're actually trying to game the system and giving those scenarios. And if your model is not performing well, then you're incorporating those things to ensure that your model is able to take care of all those things when it actually gets deployed in the production environment. About explainability, so this is basically, there are a few techniques available, right, where if you incorporate those techniques, then you would be able to identify whether your algorithm is getting biased or not, right? Or are there areas, weak points in the algorithm which people might misuse after it is gone to production, right? And that is what you can incorporate when you're building. And then there is redundancy and fault tolerance, which is more of an infrastructure thing. But if you talk about systems like self-driving cars, at the hardware layer, this is needed, right? So once your model is deployed, right, it is not that your model is going to perform the same way as it was performing in training, right? There will be new data coming in, there will be new environment, and a lot of things would be happening, right? So is your model adaptable enough to take that feedback and keep improving it itself, right? Otherwise, what will happen is you will have to take down your model, right? And this has happened with Google and other companies also. They launched something, the model was not performing well. they removed that feature, fixed it, and then again, it had to be put in production. So robust AI, building a robust AI system is very challenging. All the companies are doing a lot of things here. There is a lot of research going on. But the idea is this is a must thing to do, right? So when you are building a system from day one, you should take care of it, right? And then sometimes you might not be solving a core AI problem, right? Or maybe a part of it is solved through AI, a part of it could be solved through simple rule-based logic also, right? So you could go for hybrid architecture in which your performance, a part of the performance is coming from simple coding because that's a simple problem to solve, right? You really don't need to, if you don't have a hammer, you don't have to put something else for a nail, right? So understand where AI is required, where AI is not required. If there is something which can be solved in a better way without AI, use that in combination of AI and then build your system, right? So these are some of the other approaches. Data diversification, which is like you don't have sufficient data, your data is small enough, right? So what will you do? Augment that data, get data from other sources, generate that data automatically, right? So for example, if you want to recognize a cat and you don't have enough cat images, right? So how do you train your model? So whatever images you have, you can use those images to generate different type of cats, right? From different angles, or you could go to some open source solutions where that data is available, right? Ultimately ensure that you have enough diverse data so that your model will not be biased, right? And it will perform very well. If you have seen, there are a lot of pictures on the internet about a cookie which looks like a dog, right? And these are the kind of cases which you have to really handle at the start. Then the next part is regularization, which is more of preventing overfitting. And overfitting is you are training a model in a way that it performs with 100% accuracy in your test data, right? But when you go, it just falters, right? Because that is how the data was trained. So sometimes if your data is not right, you may think that the model is giving good accuracy and it is good model because the data is overfitting. But finally, when you deploy that, it will not work with the other set of data, right? So that is also a known problem. You can handle it upfront. Estimating the uncertainty, right? So you should understand when your model is predicting something, what is the uncertainty, right? And based on that, you can decide whether to do that recommendation or not, right? So for sometimes you would say that a 90% probability is something where the model should say yes. And if it is less than 90%, the model should not say no, or maybe there is some other rule logic that you will create, right? So understanding the limitation of your model and accordingly taking the decision. Having a human in the loop at a stage before going to production so that you can verify, take care of all these biases and adversarial conditions so that you can ensure that your model is safe, right? And sometimes you would be, because machine learning, the underlying base is all statistics, right? And sometimes you would actually be able to conclude, it's not possible always, but sometimes it will be possible to mathematically show why your model is working in the way it is working, right? And if that is the case, then you can publish your research or your mathematical explanation of how your model works, and then it will be transparently available for everyone. So what are the challenges when you are measuring robustness? What are the challenges, right? So first of all, robustness definition is very different, right? So what I have told you, the core attributes and the other attributes, different companies, different people will measure it differently. Sometimes they will take just 2 attributes because that is what concerns them and say that they have a robust model. Sometimes people will take a holistic picture and accordingly define a robustness. And it is difficult to measure robustness at all these stages because there are so many factors, right? There is data quality, there is your model architecture, then the environment in which it is deployed, right? And the interaction among all these things. Ultimately, everything going right will give you a robust model, right? So in order to measure whether your model is robust or not, it's a slightly complex, right? You can put that at different stages, different parameters and measure it. But 100% you will not be able to do it. And that is why a lot of the best companies are also not able to, handle some of the scenarios which only come after it is deployed in production. And then as you are evolving, hackers are also evolving, right? So new challenges, new vulnerabilities will keep on coming. So based on that, you would have to deploy new techniques to make your model robust, right? So because of these reasons, it is difficult. But what we can measure, so we can measure these parameters for any algorithms, right? What is your accuracy under attack? If I am giving you false data, wrong data, corrupt data, how is your model behaving, right? What are your error rates? In different models, they can be kind of measured through different error rates, but these are the general metrics, right? So precision, recall, F1 score, how is your model performing? And then there are a few metrics to say whether your model is explainable or not, which is LIME and SHAP, right? So you can use those and get these scores, right? So let's say your model is 90% accurate, but the SHAP score is not that great. And your model is 88% accurate, but the SHAP score is better. So probably you should deploy the 88%, because that would be a better situation when you go to production. And then what is your resilience to data shift? As you get new set of data, does the performance degrade? Does it remain same? Do you improve? Do you learn from the data which is coming in? And these all parameters, right? So there are some tools available. Like for example, IBM has got a tool which has a red and blue. So what you see here is red and blue. So red is the corrupt data poisoning, right? So we are trying to poison your training data, and then you're trying to protect it. You are detecting it. That's the data has been poisoned, and you are auto-correcting it, right? So this is how it works when you do adversarial testing. So there will be a red team which will be polluting your data, and the blue team which will be detecting, right? And when I say team, it is just the algorithm doing it through the techniques which are available in this library. And then these are some of the other libraries. So you have Robust Bench, which is has a lot of papers, research published on robustness. You have Robustness Gym. There is evidently AI, right, which is specifically to ML and LLM systems. This is also for generative AI. So you can use any of these tools and test your model around how robust it is, right? So this was it. I'll just stop here and take some time for questions.
Okay. That was a good insight, Arpit, and robust systems basically. So everybody is talking about AI, but if we want to push something into the production, that should be robust, I guess. So
Right.
Thank you for the explanation. But your presentation was very well explained, so not much questions. One thing is that when as you are also a CTO, right? So sometimes this might come that innovation versus the robustness. Should we stick to should we follow everything, or should we just release the product? So how do you find a balance between innovation and stability?
Right. It really depends on what is your target audience and what is your target goal, right? As I mentioned, if it's a healthcare system, you are building something, right? Robust, you cannot ship anything like that, right? You will have to get it right, tested properly and ensure that it is robust. But let's say you are building a recommendation system, right? So even if I recommend you something wrong, nothing is going to change, so to say, right? So I will learn whether you have accepted my recommendation or not. And based on that, I can improve my algorithm, but it is not mission critical, right? So if you have developed something on that side, even if you have taken 4 or 5 parameters and you have created your initial model, it is good. You can go ahead and ship and deploy and then add more parameters later on. But if it is something which will impact in a critical way, that is where you have to ensure that it cannot go to production until and unless we are really sure that it is a robust system.
That is a good approach, I guess. And yeah. So other than that, like whenever like you spoke about the robustness of the systems, right? So one more thing is that when it comes to data and AI, right? So the governance and policies are also in place. So do you have any insights on that? Like how should we take care about that? Like different countries are there and different policies are there, right? So we have to be we have to be sure about that data privacy and data security before we launch anything or before we create anything around AI or based on the data.
Right. People talk a lot about this, but I don't think at the implementation level it's really taken care of. And it is very difficult to really take care of all the aspects, right? For any AI modeling that you have to do, you need data, right?
Yeah.
Especially after LLMs, which are trained on billions of parameters, right? You need huge amount of data to really specialize in a special sector, right? And that is why you hear all these news, right? That the data was trained on YouTube videos, the data was trained on news websites without taking the permission. Or recently, Twitter has launched a feature within X, right? That which is by default on, right? So users are even not aware your tweets are being used to train their model, right? So now, I mean, ideally, in the ideal world, you should really be sensitive about if you're using users' data, take their permission and do it, right? But that is not how most companies are operating, right? So that's the ideal world scenario. But when you have some data, at least you should be able to understand that what is sensitive data out of this, right? So even if you're using that sensitive data for training, you need to ensure that it cannot be part of your model output, right? So if you're building a system which is, let's say, somehow got the data from LinkedIn of multiple profiles, multiple people, right, with some interest, and now you're recommending a person, don't share the phone number of that person to other people, right? So things like that, at least everyone can take care of, right? So,
We should take it in the consideration that where are we drawing the line?
yes.
If the information is public, then I think we should be we are like we can utilize that. But if
Sometimes
it's something like personal information, then we should stop there.
right, sometimes it is public, but then it still has copyright, right? So
Yeah.
so yeah.
Okay. So yeah, that was it with my set of questions. Like the presentation was very much detailed, not just the highlights. So I don't have much questions around that. Arpit, and considering the time constraints you have, I would like to thank you very quickly and move on with the program.
Thank
Okay.
you. Thank you,
Thank you.
everyone. Thank you.
Good night. Okay. So, hi everyone to the audience. So, this was our final speaker. This was the last speaker, Arpit. He talked about the robust system in AI. And thank you for joining. I would like to thank everyone who joined today over any channel, YouTube, LinkedIn, Facebook, wherever. You can, if you have any more questions related or you want to connect with the speaker, you can directly reach out to them over the LinkedIn, or you can send us an email with your question at reachus@cloudxlab.com. So there is one more day left, and we will meet you tomorrow on the day 5 of the Tech Week. And today, uh, as Sai, Divya, and Arpit talked about the data science and AI. Tomorrow, Gaurav Vishnoi, who is a principal architect at Cellpoint Digital, will be speaking, and Dr. Mehreen Alam, lead scientist at UrduX, will be speaking, and Sandeep Akode, who is an software development engineer at CloudxLab, will be speaking. So make sure you join, and there would be a really good insights on this. And I hope like you like the session. Thank you for joining again, and have a good night. Bye bye.